Okay, I think that following the last talk, it's my duty now that the Open Robotics has thanked all their sponsors, I get to thank them. I know that ROS has been an essential tool in over a number of projects at NASA. And I think on behalf of the community, I want to thank them for providing an even keel when I know all the effects of industry and academia are pulling them in different directions. So thank you to the entire Open Robotics ROS team, Gazebo team, for producing such fantastic middleware that's been so useful in expediting the work we've done at NASA. So thank you. Okay, so my name is Andrew Symington. I'm actually an employee of Stinger Gafarian Technologies, which is a government contractor at NASA. And I'm here today to tell you about a pretty exciting project called Astrobee that's happened over the last 4 years. Just so I get a sense, has anybody done any sort of reading? Hands up, does anyone know what Astrobee is roughly? So you've run, oh, there are a few. Okay, good. Okay, so I'm actually on the flight software team. I'm officially a research scientist, but I spend a lot of time programming and a lot of time also doing research. And we've got 6 members across our team. And today I have tailored this presentation in a way where it kind of describes what Astrobee is, kind of a few of its more interesting technical components, and then dig a little bit deeper into some of the challenges we faced with ROS and how we solved them. So without further ado, I think everybody's probably asking themselves at this point, what is Astrobee? So Astrobee is a 1 by 1 by 1 foot free-flying robot designed to work inside the International Space Station. And so for a sense of size, you could probably comfortably hug it, I would guess. The objective of this robot is to essentially provide a means for us to do some surveying across the ISS, so environmental inspection via camera, via sensors. Its second primary task is also to act as a pan and tilt camera. And so if you look at the diagrams here, you'll see that it's got a perching arm. And the idea behind that is that it can deploy that perching arm and perch to handrails on the ISS. And that way it can turn off its propulsion system, turn off its localization system, and essentially go into a low power mode where all it's doing is providing pan and tilt camera to ground station. And then the last and probably most exciting feature of this robot is that it's a free-flying scientific payload robot. So it's got 3 payload bays. So if you're in research or maybe in the private sector and you want to develop a payload and you've got some cool idea for some new interesting sensing or actuation task in microgravity, it's the platform that NASA can provide to help get you there. Now, the design of this robot is such that we ultimately don't want it to be crew-tended. So we'd like it to be able to operate remotely. I'm not going to use the word autonomous because it's not really an autonomous. It's kind of semi-autonomous because there are ground station controllers actively monitoring the robot. And the other cool feature about this robot is that it's also got completely open source flight software, and we can upgrade that software on orbit. Oh, and by the way, I've got a few references at the bottom in case anybody wants to dive a little bit deeper and read a paper on. So these slides are disseminated later, so you can read that up yourself. So it's not the first free flyer on the ISS. In fact, there have been a couple. At NASA, the Spheres project has been very successful. It was a collaboration with MIT. And in fact, the Spheres robot, and you might have seen it before, the one at the bottom right, is actually the most used payload on the ISS. The problem, unfortunately, with Spheres is over time, its lack of computational resources has become evident. It also uses CO2 tanks, so you have to keep replenishing the CO2 tanks to make it essentially fly. And it also doesn't have rechargeable batteries. It turns out getting a rechargeable battery on the International Space Station is rather tough. So the other free flyers which aren't developed at NASA are the IntBall and Simon. In fact, the most recent you might have seen, I believe, is IntBall, which is JAXA and the Japanese module. And it's essentially a free-flying camera. And then Simon is more AI targeted as an assistant for astronauts. And so you can see the images of them at the bottom of the slides. So a little bit more information about the actual hardware, because we're roboticists here, so we want to know about the hardware. If you look at here are 2 diagrams showing different sides of the free flyer. The 2 large sort of units on each side, on the port and starboard side, are propulsion systems, and I'll speak more about them later. what you'll notice is that we've got a whole suite of sensors. We have many different cameras. We have depth cameras. We have HD cameras. We have laser pointers, flashlights, signal lights. So we've got a whole suite of interesting like new sensing and UI peripherals which you can explore as you write software and it gets upgraded while on orbit. We also have a docking station. And now this dock provides the ability for Astrobee to essentially recharge, and also provides a Ethernet link so we can offload a whole bunch of ROS bags once we've taken them in flight. And then it's got its own dock controller which communicates with the robot when docked, so we can essentially wake it up, put it to hibernate it, and do a bunch of other features. So that's a kind of a cool piece of hardware as well. And the kind of state of the project, and this is the most exciting, is that we're actually having this hardware, the final certification units are being assembled. So here's a picture taken probably, I would guess, 2 weeks ago. And this is showing the fully assembled certification unit. So it's essentially a replica of the ones that will be sent to the space station. It turns out that anything that goes to the space station undergoes a whole lot of very special treatment. Like the average person doesn't get to touch it. You have to touch it with special gloves. There are a whole host of reasons why they do that. The progress so far is that the hardware's been busy being assembled to be put on orbit, and we're currently undergoing a suite of different tests. So we have to check for things that in other contexts you would need to. So we have to look at electromagnetic interference. We have to look at basic functionality. Does it work? Can we upgrade it? We have to check that it doesn't make too much noise, that if we vibrate it, things don't come apart, that it doesn't let off too much heat. And it goes through months and months and months of testing before being approved to be sent up to space. So we are probably going to launch our dock on Northrop Grumman 10, which is coming up, I believe, in November. And then 3 robots will follow in early 2019. So inside the Astrobee, we have 3 processors. We have a high-level processor, mid-level, and a low-level. The high-level processor is designed mainly for researchers to use as a kind of free platform they can run any code in. It runs Android for the sake of simplistic app development, and you interface with the rest of the system through a mechanism we call guest science, which is like an API, effectively, which gives you an access to a limited subset of Astrobee's functionality. The low-level, I'm not going to go in order because I think it's easier to describe the low-level processor and then the mid-level processor. The low-level processor would kind of be like the mission-critical processor. So we run our guidance, navigation, and control, and specifically our state estimation, and our control and actuation, as well as various signaling like status LEDs and lights. So the kind of core essential things that we wouldn't want another process that's, say, faulted or causes some crash to interfere with. And the mid-level processor is where we actually perform a lot of the flight software's heavy lifting tasks. So localization is really computationally expensive, especially when you've got HD images that you're processing. So we kind of give it its own separate processor so that it doesn't cause GNC to lock up. Now, the mid-level and low-level processors are Linux-based. They're actually ARM platforms. The low-level processor is a one board, and then the mid-level processor is an Inforce, so it's a Qualcomm 4-core ARM board, so in the low gigahertz range. And the nice thing about this is that we can use state-of-the-art smartphone hardware because we don't have to make this robot radiation tolerant, because it's operating inside the space station, not outside. So we kind of have the benefits of the shielding of the space station, so we can use this off-the-shelf hardware. Now, the diagram to the right gives you a sense for a very high-level communication diagram of how everything communicates. So MLP and LP and HLP are all on the robot themselves, and they use ROS as the communication backbone. But when the free flyer mates with the dock, it communicates over I2C. So all transactions happen over that very low-level hardware bus protocol. The dock and the MLP both have Ethernet and wireless connections, respectively, and we use DDS as our middleware. We've been doing that for a long time at NASA. Because we need delay tolerance and more control over our bandwidth usage. And that gets relayed over the KU band down to Earth, where mission ops can actually control the robot. Okay, so the exciting thing is the propulsion system. This is a new propulsion system. I don't believe it's ever been tested in any other context. As I mentioned, we have two propulsion modules, one on the port and one on the starboard side. And if you look at the propulsion module, right in the center, where I've drawn that purple arrow, is a centrifugal impeller. And that draws in ambient air from inside the space station. And then it compresses it lightly at about 0.1 psi inside a plenum. And that plenum, the air in that plenum can then be redirected through one of 6 nozzles on each side. So there's 12 nozzles in total. They're actually servoed vanes. And the neat thing is that like a quadrotor, I guess, the impellers counter-rotate to balance torque in the system. And for the sake of simplicity, what we do is we hold the impeller speed constant, and what we do is we just vary the nozzle apertures, and that's how we achieve control. Now, the complexity in this system lies that it's a fully holonomic control system, and in fact we're actually over-actuated, but the problem is that both force and torque are coupled in plenum pressure. So it means your force is not independent of torque. You have to kind of adjust for the fact that your hard limit changes based on whether you're translating and rotating simultaneously. Now, the cool thing about this is that it's completely propellantless. We don't have to send up CO2 tanks. It also doesn't have any exposed rotors, so no one's going to get their hair stuck or their fingers stuck in a rotor. And the system is rechargeable. Just when it docks, it just automatically recharges. The problem is that it outputs a very limited amount of power. So something like this, I'm not going to say it won't work, but it's unlikely to work on Earth because we're fighting 1G the whole time. And so that makes it kind of microgravity specific. Looking a little bit deeper in our control, our motion control pipeline. I'll use a laser pointer for this. Remember I said that I think everybody should be familiar with a diagram like this. It's kind of loosely a robotic control stack. We have an interesting design of our control system because we have this propulsion system here, which takes the blower speed, which is the impeller speed, and remember one of those 12 nozzle values. And we have this force allocation block. And this is a ROS node that effectively takes the desired wrench you want to achieve on the platform and then works out, it's basically got a dynamic model that works out what the correct nozzle values are to send to propulsion to achieve that. Now the controller is, I believe, relatively simple PID controller. And it takes, the command would be a segment or a trajectory you want to follow. And then you get the output of your filter, and the controller works out what wrench you want to achieve. So standard sort of control stuff. The filter, which is our state estimator, our guidance navigation system, it takes IMU measurements, propagates them forward, and then periodically corrects them with features. Now, localization I'm going to deal with in an entirely different slide because we've got several different pipelines, but I can reduce the complexity of the localization system to a set of registration pulses and features. And the reason we do this is there's a large latency between acquiring an image and getting the features out of that image. So our filter's a neat filter. It's an augmented state Kalman filter that takes into account this delay and essentially does statistics subject to this delay. Finally, the thing I want to mention is that the choreographer is essentially the orchestrator of motion in the system. So this red arrow indicates this is where high-level control comes from our executive block. So we say, hey, we want you to move this way. The choreographer then uses the planners to plan some sort of motion that gets you there, and I'll talk a little bit more about those, and then feeds it to the controller, which then forwards it onto propulsion. In parallel, we also process depth camera measurements in a mapping subsystem based on Octomap, and that warns us, because it knows what our current pose is, when we are going to potentially collide with an obstacle, and that notifies the choreographer to stop. We take a very safe approach. We're not trying replanning initially. We just want to make sure that, if we see something moving in that's going to intersect with our segment, we stop. So here's a little more information about our localization system. So we have the IMU, the RGB camera, and the depth camera. Its specifications are there. I don't need to go through all of them. You can just get a sense for what we have. The localization, as I mentioned, is split into a number of pipelines. We have 3 pipelines, which I'll go over. There are a few more, but they're basic utility pipelines, like turn-off localization and use ground truth, stuff that's not going to be too interesting. Sparse mapping we use for general navigation, and it uses features from a wide-angle monocular grayscale camera. And then marker tracking is used specifically when we dock and undock. We use fiducial markers on the dock to get a higher precision. And then handrail tracking is that we track a position of a handrail or pose of a handrail relative to us, and then we use that to perch and when we perch with our perching arm. And I mentioned that the augmented state takes features and registration pulses from those three pipelines and then fuses them cleanly with the inertial data to give us a state estimate. So general navigation, I'm going to go quite quickly through these. Again, they're paper references if anybody's interested. But the idea is that we have we're not doing SLAM yet on our robot. Just again, we're going with the option that we can test extensively and then we'll incrementally build up complexity as time goes by. General navigation, we have an offline and an online stage. So the crux of the offline stage is we gather a lot of camera images, and then we build a sparse feature map from that. So we do bundle adjustment to essentially work out an XYZ coordinate in a local frame for every feature. And then online, we do brisk feature detection using our wide-angle navigation camera. And then we find the corresponding feature in the sparse map. And then we essentially have a relationship of image coordinates and world coordinates, and world in this case is in our map, which we then feed as features to our state estimator. Docking is something that's quite exciting. So stepping back, the last localization system gives us, we're expecting in the order of a few centimeters error in worst case. Depends how good the map is, of course. But when we dock and undock, we actually have to mate with two berthing pins, which are probably about a couple centimeters across. So to get the alignment correct, we want to get sub-centimeter accuracy. So what we did is we put a fiducial marker between our two berthing points on the dock. And then as the Astrobee wishes to dock, it switches to its docking camera and then uses the LVAR library to give the pose estimates of the markers in the camera frame, and then we can perform relative localization to ensure that we have a repeatable, accurate docking every single time. Perching is a little bit more complicated because we're processing depth camera images. The crux of the algorithm is that we use the depth camera to do a wall estimation by trying to fit a plane with RANSAC. We then also use RANSAC to similarly find a line describing the handrail. And the important thing is we don't necessarily have colored points. We only use the depth camera. We haven't gone to the extent of doing extrinsic calibration with the RGB camera to get alignment of the two frames. We then detect the end caps of the handrail, and we do pose estimation of the handrail in our depth camera frame. And then once again, those are features that then get sent to the estimator, and it uses that information to localize relative to the handrail and provide a precise inbound perching procedure. So I know there are probably a few people working in planning here. So we have two planners in our system, the baseline trapezoidal planner, and I haven't got an image of that, but it really just constructs velocity trapezoids in axis angle representation for attitude, and then it's much easier to do it for translation. The neat thing about this is it's a very simple algorithm. It allows you to quite cleanly specify hard limits on acceleration and velocity, and it's kind of useful for docking and perching when you want like a really clean, exact trajectory to follow. We also have the Quadratic program planner, which was written by Mike Watterson. He works at UPenn with that fantastic Quadratic team, Vijay Kumar. And this is the planner that they effectively use to generate curved trajectories for their quad rotors in real time. And what it does is it finds a trajectory around to get from a starting point to an end point, respecting any keep in and keep out zones and minimizing overall jerk in the system. So it's a pretty neat piece of code. It's just a reasonably more complex and kind of will be used for less critical operations where we're trying to fly across between modules. And of course, there are other planners currently being written by interns and NSTRF fellows at NASA. So we've got a couple of safety mechanisms in our planning. I'm not going to go into detail here, but essentially we have keep-ins and keep-out zones, which are like prior maps, simple sort of cubic areas that we stay out of or are forced to stay in. We also build that map with the mapper, as I mentioned, which uses Octomap as a core, and then that gives us obstacle detections. And then we also, when we plan, we put hard limits on acceleration and twist. And the acceleration is fundamentally limited by how much power we can put out in our propulsion system. And the twist is limited by what we consider to be safe operating limits for the context we're working in. So I think we'll take a break from the architecture and talk more about the hardware test environments now. So you might be asking yourself, okay, so this robot's been designed for microgravity. How do we test it actually on Earth? And it turns out that's pretty complicated. We can't actually do all 6 degrees of freedom. So what we do is we have 3 different experimental setups which we use to test different problems. So the simplest is a flat sat, which just helps us test hardware and avionics. What we spend most of our time testing in right now is the Granite laboratory. And some of you might have that if you're part of a research group that does space robotics, but it's a really, really flat granite table mounted orthogonally to gravity. And essentially you have air pucks that blow out CO2, and then you float on a pocket of air. So you have 3 degrees of freedom, 2 translation and 1 rotation. We're also in the process of building a microgravity test facility, which is like a long room, which has a gantry, which is sort of like a room-sized 3D printer, with a gimbal at the end, and then that can allow us to move with 6 degrees of freedom. A big test environment, though, and something we insist all of our project partners do before they get into working with us is testing in simulation. And the takeaway point with simulation is that we've tried to design our system such that we can divide our nodes into hardware drivers and flight software drivers, and transitioning from experiments to simulation is just as simple as switching out the hardware drivers. And the only exception to this is that we don't actually simulate any feature detectors on synthetic images, because we feel that's a bit high in complexity and also probably doesn't add much value. So here's some snapshots of the simulator in action. You can see we've got the RVers, the perception, we've got the simulation, the Gazebo GUI, and then we've got the real context, which is what we test in. And I'm hoping this ends up, we have a similar analog in 2019, but we've got the perception of the ISS. We have a wonderful full ISS model, which you can use to plan paths in and do all your experiments. And then the Gazebo version, and then, again, reality, let's check back in 2019. Another important thing for us is ground truthing. We need to know how accurate our system is, especially with our localization. So we use the Vive tracking system. And if anybody's interested in like a really deep dive in how Vive works and how we wrote replacement fusion algorithms for their raw data for our context to get repeatability and accuracy, I suggest you go to Miguel Borges' ROS 2018 presentation. I mentored him when he did an internship at NASA. The initial result we're getting from the system is you can see the red and green are the alignment between our EKF and the Vive system, and that's for a planar test on the Granite table. And you can see a histogram of errors. We're looking at the mean of about 18 millimeters, our EKF. So throughout our system, we've used predominantly Kinetic. We transitioned from Indigo a while ago. We'd love, of course, to reap all the benefits of ROS2, but unfortunately we have limited resources, so that might have to unfold over a couple of years and maybe a sort of a retrospective upgrade. We also have other projects at NASA which use ROS, and they're Tensegrity and KREX, and also Geocam Space. And so if you look up those projects, that's specifically in the Intelligent Robotics group at NASA, and that's the one I work in. So now we're going to dive a little bit deeper, and I'm going to explain a couple components that we added to our stack, which kind of augmented existing functionality at ROS. So the first of which is timeouts and action. So we love actions, because all of our nodes in the system are actually nodelets. And so if you block in a service response, the rest of the nodelets in your system in a single threaded context, they all lock up. So we use them extensively across our system, but we found that we needed a little bit more control over what happens when they're timeouts. So if you don't get a response on a goal, or you don't get feedback, so we added a number of different timeouts which you can set. And so we've got our own free flyer action class which provides that augmentation for us. We initially started using YAML, but we found them a bit restrictive for parameters, so we switched to Lua. that allows us to have a lot more complex data types, and also do some light scripting in our configuration files and link variables together and make them dependent on environment variables, which we found to be incredibly powerful. We also have a config server and config client, which actually uses the existing dynamic reconfigure messages to allow us to dynamically change a node's parameters at runtime, but through the whole Lua infrastructure. We also had to augment our nodelets with some life cycle and fault management support. So diagnostic messages is great, and we do use them, but we needed a few extra things. Faults are really important to manage in a NASA project, so we had to essentially create a child class of nodelet called FreeFlyer nodelet, which adds assert fault and other common functions which we would find useful in sort of a space robotics context. And there was a bit of a challenge that happened with FreeFlyer nodelet is in a Gazebo context. You have to work out where the processes actually run. So we kind of bypass it with the setup function. I'm not going to go into details for the sake of time. Another big bane for us was cross-compilation with ARM. We did this back in 2015, so it was a real nightmare because Catkin at that point was, and I'm not sure if it still does this, somebody in Catkin should talk to me about this, but essentially writes fully qualified paths to your libraries. So we had to do a sort of a post-Catkin hook that helped rewrite all of those to our root file systems. And I've made this a lot cleaner with Catkin tools and Catkin simple, but the general idea is that this snippet of code is what saved us a lot of nightmares, and it's in our flight software. So anybody's having the same issue, I hope they're not any longer, can reference this. It's been very useful. So for the sake of time, I'm going to skip this one, and I'm going to look more at the ROS launch system. So we have a very complex launch system, and we need to have a complex launch system because we've got multiple processes launched from a single location, and often we want to remotely launch components of our system. Like we want to remotely launch our simulator somewhere, or we want to remotely launch the LLP to diagnose it as a processor in the loop problem. So like say we're running the simulation locally, but we want to run just the high-level processor on the actual ARM platform to diagnose some sort of performance problem. We had to structure our launch files in a way that enabled that. So anybody who's faced a similar problem, perhaps you can draw some inspiration from the way we've structured our launch files, and I'm hoping that they might be useful to others. And the last thing I'm going to cover is transform consistency. We don't want to have a mismatch between simulation and perception, and so it's very important for there to be consistent extrinsics between the two. And the problem is that Gazebo expects them in SDF, whereas we would normally express them as TF2 static transforms in flight software. So we had to find a way of syncing them, and I don't think I found a perfect way, but I would love to discuss. Anybody who's had a similar issue when having to deal with simulation, please come talk to me. And then the last two slides I have just covers guest science. That's the formal mechanism with which you interact with Astrobee as a project if you want to develop a payload. And I encourage anybody who has a neat idea for hardware in space or software in space to have a look at the guest science URL in the slide. And then the other thing I ought to mention is Zero Robotics. This is a really neat project at NASA and MIT. And it is essentially a competition that has kids code control algorithms for Spheres robots and then have it execute on orbit. So they first test against each other in simulation, and ultimately it's uploaded to the space station, and their code runs on a real robot on the space station. So it's very exciting for these kids, and it's a really great way to teach programming. And we're in process of transitioning from Spheres to Astrobee. It's going to be a reasonably challenging process, but hopefully it'll be more exciting as Astrobee opens up a whole new set of capabilities. Now, code is open source. I'm out of time. So again, I encourage you to check out the simulator. I was given a limited set of mission patches. Anybody knows what a mission patch is? It's what gets sewn onto jumpsuits. So I don't have enough for everyone here. So maybe I'll create an incentive. If you show me a running simulator, you can get an ISS patch. And if I still have them at the end of the day, I'll probably start throwing them out there. I have a video. I don't know, for the sake of time, if you want to move on. It's pretty short. What's the call? Absolutely. Yeah. In fact, it's only got music at the backdrop, and so I will mute the music, and then we can, of course, take questions.
question or two? I'll start. How did you approach the certification process for getting ROS used in the flight software that's going to be used on board? And if you could repeat the question for the live stream.
Okay, I think the question was how did we deal with certification of ROS to be used on board? This is more a question for management than me, but my understanding, and this is my personal understanding, is that we are not, our flight software is not marked as safety critical. We're marked safe at the hardware level. And that way we're allowed to run ROS, and it's also going to be crew tended in the first instance. So there'll be astronauts on board working with the Astrobees, making sure that everything's safe. Yes?
I got a question from the live streaming,
okay.
and two people asked the same question.
Sure.
Why you choose Lua rather than Python for your configuration files?
Well, I could deflect and say I wasn't at the project at that time, so I can't tell you. There was probably a good reason. I think there was some legacy code that we reused from a previous project, which helped expedite our progress. But that is a good question, and maybe it's something we should want to revisit if for the next robots that we develop in the IRG.
Okay, thank you.
Pleasure.
All right, for time, let's stop there. Thanks, Andrew.
Thank you.